Hey everyone, welcome to the home stretch of our linear relationships content from the Year 10 course. Now, we are looking at, in the next series of videos, probably the toughest part of linear relationships, and that is when we start to look at this idea of 3, 2, 1. Hello everyone, welcome to another video. Now, in this video and the next couple after, we are going to be on the home stretch from the Year 10 linear relationships course. And all of these videos are going to be centered on this idea of simultaneous equations. Now, these I've found often give students the hardest time. It's quite difficult, so it takes a lot of steps. So we're going to go through this really slowly and in detail in this video, and we're going to look at our first method, which is substitution. Now, as with a lot of the other videos, I'm going to take a bit of time at the start to give you guys the context, sort of what this actually means to solve simultaneous equations, and how we can go about doing this. Essentially a summary of the key concepts. Now, if this doesn't interest you, you just want to jump straight into how we can go about solving these, please scroll through to midway through the video where we go straight into some examples. But I've written here for us, now that we start our long investigation into simultaneous equations, we're given these two equations. We're given y equals 3x minus 3x plus 2 and y equals 7x minus 8. Now, what are these two things? Well, these two equations just represent lines. So they're two lines along the x and y axis in this plane, and they look a certain type of way. I'm just going to give a rough sketch of this, but this first one has a gradient of -3, so it's relatively steep, and it's descending, so when I look from left to right, it's going to be going down, and it has an intercept of +2. So, okay, that's going to look something like this, sort of, going through 2, and I'm just giving a rough sketch of what these two lines look like. This isn't an exact diagram of what these will look like perfectly. And we have, for my other one, I have a gradient of 7, so this is very steep in the positive direction, and a y-intercept of -8. So that one here is going to look something like, okay, down from -8, and it's sort of going to go up quite steeply. And this isn't drawn too well, but I just want to get at a pretty key concept here. Now, we've looked at simultaneous equations before, and we looked at solving this graphically. Now, with any two lines which aren't parallel, so these two lines that I have here, for example, they're not parallel because, as a revision from the last video, they don't have the same gradient. Anytime we have two lines in space with different gradients, they are going to intersect at a certain point. No matter how I draw these lines, maybe one going like this, one going like this, they're intersecting at one point here. Whether I do something like this and this, these two lines, because they have different gradients, they are intersecting at one point. And we will see this happening all the way through our discovery through and investigation into simultaneous equations. Now, these two graphs and any other graphs, they always intersect at one point. Let's call this point x, y, and we'll call this point x, y. So, thinking back to earlier linear relationships, when we talked about how we make these lines, if you think way back to when we did our tables of values, right when we started, linear relationships way back in year 8, we had some x, y, and we had a certain number of values of x we substituted into the equation, and we got a value of y. So the y and x changed. And when we actually went on to graph this, we would go to our xy plane and we'd say, okay, this is a point, 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 and we would make some line connecting those. Now, where simultaneous equations come in and solving these is this idea that we are finding the intersection point of two lines. We're finding where these meet. And if when I graph my lines, for example, this line that I've drawn here with all of my different points, we can think of this graph, or this line, as being made up of a series of points that satisfy the equation. All of these points, x, y. Now, looking at this picture that I've drawn here, each of these points x, y, my point xy here and my point xy here, they lie on both of the intersecting lines. So whatever this point is, I don't know what my xy is, but I know that it's a point that satisfies the equation of this line, and it's a point that satisfies the equation of this line. And the same thing here. This point xy satisfies the equation here, as well as the equation here. And because they're intersecting, they're both lying on these two lines, the point xy, these values, whether I'm looking at my pink line or my green line, the value of y at that point for each of those lines is exactly the same. And the value for x is exactly the same. So let's just pause here and reconsider our two lines up here. So we have, let me write them down here. We have y equals to, was it negative 3x plus 2? We're going to call this line 1. And my other one, y equals 7x minus 8, we're going to call that line 2. Now, when we look at two equations, we can't just solve these individually. Like, we can't find y and x in my equation 1 by moving the equation around in any way. There's just not enough information. This isn't like a regular equation we solved back in other topics where we said, okay, 6 equals minus 3x plus 2. Here we can solve this because I'm just looking for this pronumeral and I can shift everything else around. But when I'm given a linear relationship between y and x, these two variables, I can't actually work through this. Nor can I solve this particular one down the bottom either. There's nothing I can really do between y and x here to solve this by itself. We need both here. So let's do it in this color. So we need both equations to solve the value for x and y here. Now, why can we use both? Because these x's are identical. Remember, we're trying to find a point of intersection. And this point xy, the x value at that point is going to be the same for both lines. And the y value is also going to be identical for both at this point of intersection. So, this idea and the logic and intuition behind this, that's going to allow us to make a really sneaky trick in order to solve this. Now, I'm going to talk through this a little slowly just to really get this idea through. So this y and this y are the same. I know the x's are the same as well, but I also know that this equals sign means that my left hand side here is the same as my right hand side. So my y up here is equal to, another way of writing the y is minus 3x plus 2. That's what the equal sign tells us. Now this y on the bottom is equal to my expression on the right, because this equal sign tells me the right hand side is equal to the left hand side. Oops, I've done that the other way around. Tells me my left hand side is equal to my right hand side. Now, if these two y's are the same, and they're both the same as the things on the right hand side, we can then say, well, these two things on the right hand side are exactly the same. So in other words, I have y equals minus 3x plus 2, but that y is the same as the y that is equal to 7x minus 8. So therefore we can say that these elements on my right hand side, minus 3x plus 2 and 7x minus 8, are the same as well. And this is where the idea of substitution comes into play. So I have my thing here, y equals minus 3x plus 2. I have my expression. Now I have y equals to 7x minus 8. Now you remember way back when we did algebraic substitution, or even my table of values, substituting means putting one thing in place of another. Now, since I have this y and this y, and I have an expression of my y down the bottom as 7x minus 8, I can put that in place of this guy here, because my y's are the same. So let's actually go ahead and do that. So these two are identical. I have substituted in my expression for y on the bottom line, that second line, from my second equation, into the y on my top equation to get my two right-hand sides being equal. This is the trick for simultaneous equations that we can use based on this fact that these lines have a unique value x and y, in which the y is equal for both lines and the x is equal for both lines. And now we can just go ahead and solve this equation. Why can we solve that? Because we have only one pronumeral now. This little piece of manipulation allowed us to make an equation with two expressions, y and x, and condense those two equations into one, which has only x. And now we can just solve this like we would a regular equation. I want to add 3x to both sides here to group the x's together. And I want to add the 8's to both sides to group the regular numbers together. So on my left-hand side, I get 7x plus 3x. That gives me 10x. And on the right-hand side, I have 2 plus 8, which gives me 10. And now, finally, I have 10 times x here. I want to divide both sides by 10 to undo this multiplication of 10 with x on the left-hand side. And I wind up with here, x equals to 10 divided by 10. That gives me 1. Okay, so let's look at what we've actually found by doing this. If we consider these examples here that I drew, now these aren't necessarily the lines we had, but we have found the x value that both of the point that both lines live on, where they intersect. And if we even look at this rough sketch that I did, we have found the x value out of this point of intersection. And now, since both of these equations touch x equals 1, so since x equals 1 is a value on both of these lines, then if we substitute that back into each of my equations, I'm going to get a value of y. And because both of these are identical, I can either substitute this into equation 1 or equation 2, and I will get the same value for y. Let's actually just check that. So I'm going to sub x equals 1 into my equations 1 and 2. Okay, so putting this in, I get, let's do a different color. For my first one, I get y equals minus 3 times 1 plus 2. And that gives me minus 3 plus 2. That gives me minus 1. And my other one, I have y equals to 7 times 1 minus 8. 7 minus 8 gives me minus 1. I get the same thing no matter which equation I substitute into. Now, why does that work? Because this is the intersection point. That's where both of these values, x and y, are the same for both lines. And if I look here, I mean, I haven't drawn it very well, but that's kind of roughly where these were to intersect. My x coordinate is 1. My y coordinate is negative 1. So before we looked at solving these graphically, now we are looking at solving these algebraically or mathematically, which is a little bit harder, but all we are doing is that we are making x or y the subject of my equation. And then when I have my y's on one side equal to another side, I can set the two other sides to equal each other via substitution and via this idea we talked about before of these intersecting points and the x and y values at that point being exactly the same. Now let's try one more question, and I'm going to look at this a slightly different way, because with substitution we can either make both maybe x the subject or y the subject, then just set them equal to each other. But we can actually do this in a variety of different ways. And we're going to show this with our last question here. So if I have, and I'm going to make this one a little bit trickier. My first equation is 2x minus 3y equals to minus 8. That's equation 1. Now equation 2 is y equals x plus 3. Okay, now this isn't super obvious, and the method you choose is going to depend on how your two equations look. Let's look at what I have here. Now, in all of these ideas of finding the intersection point of two linear relationships, two lines, we are always looking at this idea that these y's are the same and these x's are also the same. Because where those two lines meet, the x and y values are the same for both of those lines. Now, we can rearrange this and do it the same way as we did at the top, but let's just think of another way we can maybe do this. Feel free to pause this video and have a think about how you could maybe do this, but looking at this idea of substitution, I have an expression for y in my equation 2. And that y is the same as this y up here. So couldn't I just put my other way of writing y, because remember we have an equal sign here, I can also write y as x plus 3. Why don't I put that x plus 3 in place of the y? Because it is exactly the same. It is equal. So what we're going to do, we're going to substitute y equals x plus 3 into equation 1. So I'm putting x plus 3 in place of the y. So what am I going to get? Well, in my top equation, I'm going to get 2x minus 3. And instead of the y that's multiplying by the 3, my 3 is going to get multiplied by x plus 3. And that gives me negative 8 on the right-hand side. Now look at what we've done using this little trick. My two equations with x and y variables in each, equation 1 or 2, we can't solve these one by one. We have to do something between those two equations. And that is this idea of substitution. I have a value of y that is equal in both of these equations. That's why I've color-coded these. And one of my y's is expressed in terms of x. So that I'm going to put in place of the y in equation 1. So this y in equation 1. And now I have all x's. This becomes an equation I can now solve. So in order to do this, well, I want to first expand these brackets here. So my 2x stays how it is. I have minus 3 times x, that gives me minus 3x. And I have minus 3 times positive 3, that gives me minus 9. And I get negative 8 on the right-hand side. Okay, and now I have these two like terms here. Now, algebra tells us I can work with these. So 2x minus 3x, I can write as negative 1 lot of x, or negative x. Minus 9 equals to minus 8. Okay, so now I just want to solve the equation. So I can add my 9 here. That gives me negative x on its own. So I get negative x equals to minus 8 plus 9. That gives me 1. And minus x equals to 1. So I can undo this by just dividing by minus 1 on both sides. Because this is like saying minus 1 lot of x. So dividing negative 1 by negative 1, that's going to cancel these out, leaving me just x on its own. And I get negative 1 on the right-hand side. And now that I have an expression for my x, I've found this value of x that is the same in equation 1 and 2. So I can substitute it into either, and I will get a correct value for y. Now, when you're choosing which equation to sub back into, because you just want to sub it into one, you won't be expected to do this to both, because they're going to give you the same answer. That's for y. That's understood. So here we're just going to pick the path of least resistance. What would be an easier equation to substitute x into? Well, I don't know about you guys, but equation 2 seems far easier, because if we did it to equation 1, we'd still have to move some things around and it would get pretty annoying. All we have to do for equation 2 is substitute in negative 1 for x and add 3 to it. So let's just do that in our working out. So I'm going to sub x equals minus 1 into equation 2. And I will get y equals minus 1 plus 3, I think it was. Yep, minus 1 plus 3. And that's going to give me the point of 2. So, in doing this process of substitution, this assuming that where the lines intersect, their x and y values are the same, we can therefore say the point of intersection, or the solution to the simultaneous equation, a value of x and y that satisfies both equations, this is the point -1, 2, where the -1 is the x solution I found by substituting in, and the y I found once I got the x, substituting that back into either equation to get an answer for y. That's our point of intersection and our solution to both equations. So this is how we can use substitution, and we'll be looking at another method in the next video called elimination. And for the final video of this series, we're going to put all of this together and look at some harder problems, some worded problems relating to these simultaneous equations. But thank you so much for joining me today, and I will see you in the next video.